Hello, welcome to this new webinar. Today we will talk about the assessment of thermal effects in concrete structures with CivilFEM powered by Mark. The webinar host will be Roman Martin and myself, Ronald Siat. The summary of this webinar. The goals will be the finite element analysis for assessing the thermal behavior and structural response of concrete structures by means of two examples. One will cover the risk of early age concrete thermal cracking and the fire safety assessment. As well, you will see the importance of restraining and the effects of the boundary conditions, plus with their final recommendations of good practices. Yes.
We are going to see today two examples, as Ronald said. The first example is the early age thermal cracking on a foundation block, as you can see here. Well, in this foundation block, we'll have the concrete curing temperature, the temperature, the heat that is generated by concrete maturing, and we'll have the thermal expansion of this concrete block plus time-dependent properties. The cracking stress will vary with time. And of course the restraint and plus reinforcement effects on cracked patterns. And the second example will be the fire safety assessment on a tunnel lining segment, and we also will analyze the boundary condition influence.
The software to be used is CivilFEM powered by Mark. It's a high-end general purpose finite element software, including advanced analysis capabilities, and suitable for all the needs for civil and structural sectors. It's developed based on Mark as solver and Mentat as measure, which is one of the world's most powerful nonlinear solvers, provided by Hexagon company. To simplify and enhance management of civil engineering structural and geotechnical analysis.
Well, CivilFEM powered by Mark has a lot of features. Most of them are related with civil and geotechnical engineering analysis. Of course, there are a lot of tools for ULS and SLS design of steel and concrete structures based on codes and standards, calculate reinforcement amount or calculate checking by Eurocodes, ACI codes, and many other codes. And it is also to these capabilities, it is added some of them advanced nonlinear simulations focused on geotechnical analysis, and also seepage structural or thermal couple structural analysis, thermal structural couple analysis. Today we are going to focus in this last advanced capability, the thermal structural couple analysis.
Yes, the features of this type of analysis are the properties, thermal orthotropic material properties, including thermal conductivity and specific heat, nonlinear behavior of the material, including the temperature and time dependent properties. Of course, the boundary conditions according to convection, conduction, and radiation for any type of elements, and a nonlinear steady state and transient thermostructural coupled analysis is included, and you can process results for this kind of heat transfer analysis.
Well, this the first example we are going to see is the early age concrete thermal cracking. In this model, we will have solid elements for concrete, also thrust element for rebars. We are going to analyze two different models to compare results between reinforced and non-reinforced concrete model. And of course, the analysis type is a transient thermal structural couple analysis. The nonlinearities that we have are the concrete nonlinearities, of course, thermal expansion and time-dependent properties, especially the crack stress, the cracking stress that is a time-dependent property. And the boundary conditions, in this case, we'll have in this block the ambient heat exchange that could be through the formwork that is on the sides of this model, and on top is the ambient heat is through air, so there are different filming coefficients, and the mechanical support is the base layer on the bottom that is all concrete with a higher stiffness, and underneath it there are fixed mechanical boundary conditions. So if we open the software, we can see here the model. These are two different blocks. This first block has the heat generation. So here, if we see in the software the boundary conditions that are applied, this is the flux boundary condition, and here we can see that this is associated to this block, to this volume, and it is the input is the volumetric flux table is this one that is a time-dependent table. So the input is through hours, it could be minutes, anything, and well, this is the chart of the heat generation that is from 0 to 120 hours. That is what we have solved, 120 hours for this model. So well, this is the heat generation from maturing of this concrete block. This is an all concrete, so it is not generating any type of heat, but there is a contact between them with a heat transfer, and also the other boundary conditions are the convection air boundary condition. So here we have different filming coefficients, and in this table we have the ambient temperature. The ambient temperature is this one, so there are different values between day and night, and we are going to solve these 5 days, 120 hours. And the same for the formwork on the size of this element, this model, and so here we can see that we have different filming coefficients and different boundary conditions on both sizes. Also, this formwork is generating a mechanical boundary condition that has been modeled through springs. So these springs, we can find them here. For example, if I plot this spring on the mesh, we can see how it is generated. So well, it is a simplification of the model, but it can be modeled in different ways. We have added these springs, and this formwork can be removed during the analysis. So well, in this model we have solved for many different days. Well, hour per hour we have solved the model, and the material properties here we can see for concrete. This is the old concrete, the new concrete. Here we can see that this is a non-linear material behavior. This Finite has isotropic plasticity compression model, and for cracking it is a Nage dependent property. In CivilFEM we can add a constant value for cracking stress, temperature, or age dependent properties, and here we have a table for every hour a different value, and we saw the chart how the cracking stress is increased during time. Also, the rest of material properties are time-dependent material properties. So also for compression, we have different compression parabolic loads for the analysis diagram. Here we have for different days, and CivilFEM interpolates for this. So we have this chart, this stress-strain relationship. And also to this nonlinear model, we can add also creep and sink rate behavior. So by The most important part of this model is the heat transfer analysis, the heat generation from concrete maturing, the ambient temperature on the different phases of this block. And also in this block we have modeled just one quarter of the block. So we have added symmetric boundary conditions on all the sizes, and this is very useful to see the internal temperature of this model and also internal cracks on this model. So well, if we go back to the PowerPoint, we can see a video that CivilFEM generates for the evolution of temperature in this model.
Okay, here you can see in this chart the graphs of the different points of the model, top, middle, and bottom, and the evolution of the temperature inside this block. As you can see, and below you have the days, the hours, and in ordinate you have in y direction you have the temperature in centigrade.
Well, and also in previous slides we have seen the temperature the evolution for time, and in this plot we are plotting the cracks. In this plot, this is the last after 120 hours, the last result we obtained, and we can identify two different types of cracks. The surface cracks. These surface cracks are due to temperature gradient, the gradient that is generating between when the temperature increased inside the model, and there is this increase on temperature inside the block increases deformation outside and increases stresses outside. So these surface cracks are generated first, and they are generated when the heat is increased inside the model. And there are other cracks. In this case is one, but we could have several ones. These are the deep cracks, and these are more related to external restraints. These external restraints, that is due to this base of this block, the stiffness is higher, so during cooling, also synchrate effects or other concrete effects, this generate a shear on the base, and these cracks that are cross-section cracks could cross all the section. For these foundation blocks, this could happen horizontal in this way. For walls, vertical walls, these cracks could be vertical and could cross the whole element. And this is more related to concrete cooling. So these deep cracks happen after the surface cracks, and they are much more dangerous. If we see in this video, we could see the evolution of cracks. We can see that first surface cracking are happening, and then suddenly the base cracks appear after the surface cracks. So in this other example, in this other plot, we are comparing the two different models we saw before. The model one, which is unreinforced concrete, so there's no reinforcing bars in this model, and in the second model we have reinforcing bars on the surface. As we can see, the reinforcing bars are reducing a little bit, reducing these surface cracks, so the value of these crack widths are smaller, but they don't have a very big influence in this section cracks that happens in this. And in this plot we are seeing the stress in reinforcement.
Okay, these are the details of the next example number 2. As you can see here, they are applied the temperature dependent material properties taken from Eurocode number 2 and Eurocode number 3. These are the thermal conductivity and the specific heat, which are depending on temperature, as you can see in these charts, as well the compression stress versus strain is in this table, in this chart. Okay, then the thermal actions in case of fire from Eurocode number 1, and different boundary conditions will be applied, and we will see the different results. This
Well, this example is based on a paper. This is the paper we used, this numerical investigation of a reinforced concrete tunnel segment subject to elevated temperature via a finite element model. In this paper, they analyzed this tunnel lining. So we have generated the same model, and in this tunnel they have in this example, they have applied vertical loads on a segment, and then applied temperature on the bottom, and they have analyzed different results of this model, and they have also compared with another finite element software. So what we have done is this example is starting with the with this example, just comparing CivilFEM results with these real results obtaining, but we have gone further, analyzing a little bit the influence of different boundary conditions. So well, as well here, as you can see, for this in this model, first we have applied a fire on the bottom of this. Well, this fire is applied after 5-minute loading on top. So here is, if you see the model, we have first applied some structural loads at 1/3 of the radius, and then after that we have applied the fire boundary conditions on bottom. These fire boundary conditions on bottom on this part, and we have applied different boundary conditions on these sides. Here we can see that also the in this it is quite important, the heat transfer analysis. For concrete, we have used these heat transfer properties. For the thermal conductivity definition, this is the table that we have used. This is the Eurocode definition. Also the same for the specific heat, we have used this table, and also, sorry, we have used this table, and also for steel we have used these other properties. This is the function of related thermal conductivity, and in this other table we can see the specific heat that is temperature dependent properties. So well, with this basic model, we have applied different boundary conditions. These different boundary conditions was simply supported at both ends, so it could, at this end, it could have displacements and also rotational. Another boundary conditions that we fixed the radial deformation, so this block could not have displacement on the radial direction, on the circumferential direction, but we released the radial direction, so the radial direction was free but not the circumferential. And another intermediate result was with another model. Here we have the other model that is an elastic connection. This elastic connection is through these bolts that are connected here through these holes. So these bolts were connected to the rest. Also here we can see we have the reinforcement groups, bending and shear reinforcement groups. So we have applied 5 minutes boundary conditions. And so well, in this model, what we can see is the evolution of the model for time. So if we plot the results, and in example we plot vertical displacement of one of these nodes an example node from here, top middle, So well, here we can see if we applied at that point a vertical load, we can see that due to this vertical load we have a vertical displacement. So with some crackings for the first five minutes, then when we apply the heat, then the heat what generates a thermal expansion that moves the segment upwards, and finally it starts collapsing, and the displacement is downwards until the collapse of the model. So well, if we see the slides, we can see, we can compare. We can see here some results that depends on the boundary conditions. We have the failure of the concrete, these cracks under the loads with the negative, when the positive bending moment is higher, and we have these cracks. Also due to the negative bending moment that supports in case of completely constraints or flexible supports, we have these other cracks, and also some yielding at both supports and at these points on steel. In this plot, we are also plotting the compression yielding on this part due to the compression failure, the concrete compression failure. And well, in this last example, we are going to compare the three different options. In this case, it was flexible connections where crackings are happening at 1/3 under the loads, and also in the supports. We have positive and negative boundary conditions. In the next one, on the right, what we have is with another boundary conditions that is pin simply supported and cracks only happen here. And in this other at the bottom, we have completely constrained boundary conditions. With this completely constrained due to the loads, we have compression on these zones, and the thermal loads are generating cracks on top. So it depends on the boundary conditions. We have different behavior of this tunnel lining, and different stiffness, different time for the collapse. So well, these boundary conditions depends a lot on the ring effect, and the joint behavior of this tunnel lining. So also with CivilFEM we could model the total rings and the ring effect and the joint effect with the whole circumference. The previous examples were more based on that paper, and it was used to compare CivilFEM results with the real test that were done. And also with CivilFEM, we could analyze not only the ring effect but also the construction process. In example, like this example, that this is a tunnel construction where different line segments are placed on this after the excavation with a pressure on the front of the excavation. And also in this model, we had non-linear material models for the soil, and also a building on top, and we could obtain the displacements and the possible vibration analysis on the building and the possible affection on it.
Okay, so after these examples, we proceed with a summary of all the concepts and aspects of this webinar, which are well, the thermal behavior of concrete structures, including the convection, conduction, and radiation boundary conditions, and of course you can add as well the boundary conditions for the structural analysis. The applications of these analysis are, as we have seen, an early age concrete, both maturing temperature and thermal cracking, fire resistance, and solar radiation, which wasn't explained today, but of course it can be developed in CivilFEM.
Well, what we have seen in these examples is the suitable or the finite element analysis for analyzing the behavior of concrete structures and base it not only in nonlinear material properties and thermal time-dependent and temperature-dependent properties, but also the influence of restraints and boundary conditions, and how we can obtain a really detailed analysis and behavior of concrete structures for improving our designs. And the most important part is avoiding collapse of the structures and increasing ductility and avoiding this type of collapse and problems in concrete structures.
Okay, thank you very much for attending this webinar. Of course, you can place your questions or any other doubt you might have using the survey that will pop up once we finish this webinar.
And of course, if you would like to use and to check CivilFEM, you could ask us for a trial version or a student version would work that you could download and use it. Also, of course, you could ask us for these examples, and you could practice and learn much more about this thermal structural couple analysis. And please do not hesitate to email us to ask for further questions, because this is a short webinar and we couldn't explain in detail, but please do not hesitate to email us and to ask any doubt you could have about this webinar. Thank you for your attention.
Bye-bye.